So I'm Carol, and like Adam just said, I work at Buzzfeed. So most of you probably know what Buzzfeed is, but if you don't, I'll give you a quick overview. So Buzzfeed is a media and tech company, so we produce a lot of content, and then we distribute that content over a variety of platforms. So some quick stats. We basically get a lot of views on Snapchat, YouTube, Facebook, and in general, we get 9 billion total views a month. So the tech part really comes into how we take the content that our editors create and how we curate that so different audiences can see different things that they're interested in. So all that's to say, we have a lot of views, but obviously we do want to keep growing. So that's kind of where me and my team come in. So I am on the network growth team, so our goal is to just keep growing the website. So BuzzFeed has a lot of different destinations, but our goal is to grow across all those destinations, not just news, not just Tasty, not just any of our other media brands. So there's a couple of like extremely simple ways you can think about growth. So one is to, I guess, increase your user base in general, and then another is to basically increase how your users interact with the website. So this talk about like related content will be mainly focused on the second. So surprisingly, like when I joined, I was really surprised that we didn't have any related content. So for example, like, and this is actually something I used to do, I would kind of look at different ways to decorate my room, and I would be interested in seeing more content about that. But then if I looked on the different recirculation areas of our website, none of that was relevant at all. In fact, the other recirculation units are populated, there's a number of ways they're populated, but some of them are based on click-through, some of them are based on the number of like incoming traffic they're receiving over a specific time window, some of them are just like reverse chronological. So the only way that you could find related content was if an editor chose to manually curate some links and put them at the bottom of the page. But that obviously is kind of not the best way to go about it, since we have a huge content library, so editors don't necessarily know what is the best thing to put there, and they also might bias towards their own work. So that's kind of why we realized that it'd be a good idea to have an automated way to generate these things, and we also hypothesized that doing so would increase our pages per session and also how much time our users spent per browsing session. So just to give like a little bit more historical context, like I started on the As-Is team, which is like our beauty and style destination, and when we talked to our editors, they also had like this similar suggestion. So I originally started working on this model using as-is only data, and so my training corpus was only like a few thousand at the time, so that kind of, I guess, informed how I went through the process a little. But basically, I created the model with as-is, my corpus grew, so our results got a little better. Then I ended up moving to like all of network growth, so then I expanded the model to just like more of the website, and then eventually we productionized it. So I'm just gonna kind of go over which models that I considered and then give like a pretty high level overview of them. So in our case, like we were just interested in figuring out like overall content similarity. So for like any text processing task, you're basically trying to find out how you can convert words and other documents into vectors, so that way you can compare them numerically. So there's a lot of different ways to do that. There's count-based methods and predictive-based methods. So for count-based, you would basically be computing like count statistics, so like frequency, co-occurrence, and then basically reducing them down to get a dense representation of each document. And for predictive methods, you would actually be trying to predict the word or their neighbors, and then learning embeddings that way. So I chose to look at Word2Vec, which is obviously very popular, fast text, doc2vec, and then 2 topic models. So I think it's like easiest to start with Word2Vec because so many things, well, at least the other 2 models I used are very closely related to them or related to it. So Word2Vec, it's basically a shower neural network. It's trained on a task, and you use the hidden layer as your embeddings. So it's kind of similar to how if you have an autoencoder, you use like the hidden layer to basically represent like a condensed version of your input. So you can either train a word-to-vec neural net using the skipgram model or the continuous bag of words model. So in the terms of skipgram, you're basically trying to predict your context words given a target words, and continuous bag of words is the opposite of that. So given what we learn from this, as you can imagine, because we're learning about the context, what you'll have is, in theory, you'll have embeddings that then are similar for words that share similar contexts. One really interesting thing about this model that also made it like so widely used is that it's really computationally efficient. So instead of having, there's like a couple of techniques. So you didn't have to update like a huge set of like hidden layer weights using like negative sampling. So basically only updating like a small sample of weights based on how frequently words occur. So you can kind of like from word-to-vec, I think they're just like follow-up papers and like methods written for doc-to-vec and fast text. So doc-to-vec is, it's basically like word-to-vec, but you're adding in document context. So you're adding in a document ID. There's also two variants of it, distributed bag of words and then the distributed memory model. So one of them includes a document vector as part of the input layer and learns the document concept through training. And then the other one, you basically have an input layer of only document IDs, and you learn a document vector based on being trained on predicting like the probability of words that occur within that document. And then the other one, fast text, is one that I wanted to use because, as I mentioned, I had a very small training corpus, and so like I didn't have like a whole, like there are some words that occurred like very infrequently, and fast text, because it doesn't treat a word as like a single entity and learns more subword information, I figured it was like a good model to test. But basically, fast text represents words as the sum of their n-grams, and you can see like an example of the n-grams of where in the slide. And then quickly just going into topic models, which were the last two models that I tried. And the reason I did topic models is because word-to-vec and fast text, they both give you word embeddings, but in my case, I was really looking for like a document embedding. So that's why I used doc-to-vec and topic models to get document vectors. So we can probably just start with like LSI because it is, I think, a bit of the simpler of the two. So you have a sparse document term matrix, and that can just be like represented with counts or with their term frequency and first document frequency values. Then you can use singular value decomposition to decompose that matrix into a document term matrix, the singular values, and a term topic matrix. So then when you have your document term matrix, what you have is then your document represented as a vector of your, like with the probabilities of all the topics within that document. And one drawback to this is that you can't really interpret what those topics are, so that kind of leads you in to the next one. So LDA is just, actually I think it's easier to describe like probabilistic LSA, because LDA is basically a variant of that, but more or less you are generating your document topic matrix and your word topic matrix based on a probability distribution. And so LDA then attempts to generate your original matrix using those probability distributions using a different prior. But what you do have is you do have topics that you can interpret, but also like you get a document that's represented by the topics and all the probabilities within. So I have all these models, and here's kind of a summary of how they all performed. So I was kind of lucky in that we did have about like 1,700 articles that had editor curated links for them, and those were mostly all news articles. So I did think those would actually be pretty relevant because the writers of news articles generally are kind of like experts in, I guess, what they're writing about, and also because news topics are more timely, like they don't have to worry about like sorting through like a huge corpus. So I kind of looked at this in terms of precision, recall, and then also like the general ranking of where editor generated recommendations ranked in my list or in the model generated list, and then also the number of articles where at least one of the recommendations from the editor was found in the model generated recommendations. So as you can see, the highest performing models were a combination of the word embeddings mixed with TF-IDF. So just a quick point about the word embeddings, a common like industry baseline is just to average all of the embeddings and turn them into a document embedding. But that worked okay for me. But I also instead weighted the word embeddings with their TF-IDF weights, and that worked out a lot better for me, not just looking at these metrics, but I also read through like a lot of the recommendations on my own. So I also did a T-Sne visualization. This isn't going to be super helpful, but you can kind of see what the clusters are. So like the yellow cluster here is like, or the blue cluster here is like shopping content. I actually kind of forget what this one is. But then this is recipes, and then there's Harry Potter. The brown up top is like politics. So they all like were definitely easy to be interpreted if you actually like kind of like look through the titles. And if anybody wants to see the plotly, just please ask me. So then in the end, our final model was just a word-to-vec model embedded with an embedding size of 160, combined, and it formed a document vector using TF-IDF weights. And I guess I didn't really mention what data I used exactly for each of these documents, but I used the Buzzfeed title, the little like byline blurb description from the author, all of the text, and then I also enhanced it with like some of the tags that editors used. And that just basically became the post metadata that I used to train all of this. So here's like an example of some of the recommendations. Infinity War stuff. I also included one of the ones from quizzes because the model actually does work pretty well even when there aren't that many like words within the article, which happens a lot to us for quizzes and for a lot of like BuzzFeed original content. So now we can just kind of talk about how we went to production. So one of the biggest challenges here was that the service that we deploy and run most of our services on at BuzzFeed has like a 3 gigabyte memory cap. It might be 4, but either way, ours exceeded that. So for the batch training part of it, we ended up running it separately using like a Google Cloud instance. And so what happens is that we pull all of our post metadata from our BigQuery database that is not updated real time. So we have one process that batch trains on everything in BigQuery, and then we have another process, which is a queue reader that basically captures all the buzzes like in between training times. So during batch training, we develop the word vectors, the TF-IDF corpus, and then the phrase model that we use as well. And then we store all of those components into S3. Then the queue reader listens for an event every time a new post is published, and then it reads from the same S3 model, the same S3 bucket, and it grabs the vectors, the TF-IDF component, and the phrase component, and then it generates like recommendations based off those saved models. And then also whenever we update any of the model files, the queue reader itself will automatically know to like reload. So it's always consuming like the most recent copy. And then after that, basically what the model comes up with is we send another file with all of the results to our orchestrator API, which then stores all of this in Redis and makes it available for the website to like pull all the stuff it needs to render. So moving on to some results, finally. Here, we ran an A/B test over 2 weeks. It was kind of on like a smaller subset, so we only ran it for BuzzFeed original content, so that didn't include any like quizzes or Tasty or like news, any of our media brand stuff. And we ran it for US edition only posts. But in general, we did observe significant results. So we ran it for like a number of metrics, but I felt like pages per session and time per session were the ones that we wanted to test the most. We definitely saw like more of an impact on desktop, which is not like extremely surprising since our users on desktop tend to have longer sessions anyway. But in any case, all other metrics performed pretty well, including just like the number of visits that the user had over that time, the number of sessions the user had, like not just within the session, but over the entire test period. So we ended up like rolling this model out. Oh, and then another quick thing is we tested it with 2 different variants, one of them below our share bar and one of them above. That was just to make sure that like our share metrics weren't affected too much, because the idea was maybe if you click on one of these things, you forget to share an article you meant to share, but there weren't any impacts there. Okay, hopefully you can see that all right, but these are basically the click-through rates for the different units that we have on our webpage. So the related content unit is the blue line, and it currently has the highest click-through rate out of the other recirculation units on the page. And after the A/B test, we also rolled it out to all English posts, still excluding any media brand stuff. And we're currently seeing about 300,000 clicks per day. We're also going to be expanding it, I think, to our app users, because right now this is only on BuzzFeed Web. So in general, what we've learned is that like people do, in general, like they like seeing related content, which is not an extremely groundbreaking observation, but it ended up working out pretty well in this case. But there's a lot more work that we want to do with this. There's like a lot of other word embedding and sentence embedding models that like I've wanted to try to improve some of these a little bit. And we also, a big thing that I think is really important is adding like more diversity into these, because right now when you go onto the website, you'll see articles that are like very, very related, but you might get tired of like reading about ways to decorate your room or buy more clothes or something. So in general, figuring out how we might be able to use these vectors, but also figuring out a way to show more diverse recommendations is really important. And also we might be able to use these to help improve some of like the personalization we still have right now. Right now we use like a collaborative filtering personalization method, and I don't think it's very well tuned for the cold start problem. So we might be able to combine these with that. And then lastly, it would be great to also rank some of these, not just based on similarity, but also based on how they're clicking. But right now, the way we have our website tracking set up, we are not quite there yet. But in any case, there is a lot more we can do with this, and we are all very excited. So that is everything on my end. So thanks.
Hello. For your point you just raised at the end, have you looked at all for your users? Are they interested in the same types of content, like the person who's interested in fashions, also interested in politics, so recommend that?
So no, we haven't, but that is kind of what I was thinking about next in terms of introducing diversity. So what I was thinking was basically using the document embeddings, clustering them, and then looking at which like topics were grouped close together, and maybe recommending something after that. But that's definitely like something that we are thinking about.
Hi, thank you for the presentation, first of all. How often would you train your model?
We only train it every other day because right now the corpus is like 66,000 articles, and so like the weights won't really change that much unless we're introducing like a lot of new vocabulary. So every other day might even be like not necessary, but yeah, we don't train it daily though.
So have you noticed for certain like genres of articles, this engine not performing very well? Because like when you start creating these vector embeddings for each word, they kind of like capture these words all fit within the same context. But if a certain genre has words that come from like various different contexts in general, all from across your whole website, the average will actually not represent what the article is about anymore. So I'm just wondering if you've seen that in any place or observed that behavior.
So do you mean like the quality of the recommendations failing in certain types of articles, or the performance of like how users interact?
Yeah, so like the quality of the recommendations for like specific genres not performing well, and like have you like had to deal with that issue?
So I did see that a lot when I was using averaging, especially for like our culture related pieces. So like the averaging worked really well when it was about just like a lot of like a concentrated list of how to do the same thing. But if you've ever seen like a BuzzFeed list post, it can be like extremely random. So averaging, like I definitely saw it not working out very well for a lot of those things. But when I applied the TF-IDF averaging, like I see that a lot less. I guess like some places where the only post I've seen it do really poorly for is posts that have extremely sparse text. So we've just like introduced like an interactive way to like pet your post or something. It's about like dogs, and either way, like the only word is like dog. Actually, it's doggo and pet, and so it doesn't do. Oh, and pant. So then it recommends a bunch of stuff about jeans, which obviously doesn't make any sense. So.
Cool. Nice.
Were named entities, like people's names, for example, important factors? And did you find any embedding strategy to be more successful dealing with that?
So what I did do is I compared using, not using like a phrase model to detect common phrases and using one. And so I definitely, because for word2vec, as you probably know, like you pick like a window, but the position of the word within that window doesn't really matter. So using like the Fraser model helped a lot with like named entities, because we do have a lot of posts with like celebrity content.
Hi, I would like to know if you have especially handling the really time window of the recommendation. Let's say during the Christmas time, maybe Rockefeller Center talk about Christmas tree, but in January, you don't want to show that content anymore. Do you filter it by maybe by label or by genres? So unfortunately, we don't do that right now, but that is one of the things that we want to incorporate recency. So we do have another like evergreen model that detects like evergreen posts. So we're basically trying to apply those tags onto here, because that is like a problem that comes up, not so much for like holiday related things, because people mostly read holiday related things around holiday times, but it comes up for like timely like TV show content, for example. So we're basically, so yes, we do want to start filtering it so that like you can only really see like evergreen recommendations.